previous lessons, we learned about how acid and base is measured using the pH scale, and the pH scale is ranging from 0 all the way to 14. And we know that right in the middle we have 7, that is our water, the neutral pH. And from 7, if we're going towards 0, it is becoming more acidic. Or if we have 7 to 14, it is becoming more basic, okay? And when you have an acid and a base react with each other, they neutralize each other, and in the process they form a salt and water, which give us the pH of 7. Now, in this lesson, we are going to apply that same concept to a lab technique called titration. Well, what is titration? Well, we saw the term titrated before. Using this technique, you can actually find, using the method of titration, basically, if I have an acidic solution that I don't know the concentration to, or if I have a basic solution that I don't know the concentration to, what I can do is applying the knowledge where acid and base react and neutralize. From there, we can solve for the concentration that we don't know about that acidic or that basic solution. So here is the apparatus or the setup of titration. I have myself a flask, and this is the burette. And in a flask, I have, in this example, I'm going to look at an acid solution where the concentration is unknown. So we don't know the concentration of this acidic solution. So what I'm going to do is I'm going to react with the base. And for the base solution, I know exactly what is the concentration going to be. Because once I have the volume and the concentration, I can find the number of moles. And there we can use stoichiometry to solve for this concentration. Well, of course, we know exactly what is the volume of this acidic solution with unknown molarity is going to be, as well as for the base, we know exactly what is the initial volume, okay? So the initial volume of the base with the unknown molarity is going to be. And what I'm going to do is, before I put in any of the base into the acidic solution, I'm going to add in the indicator. So I'm going to add indicator. Now, what are indicators? Basically, how it works is that there are multiple indicators. And most of the indicators are weak acid, okay? And what's so special about this indicator is that notice how different indicators have a different color, and this color happen in a range of pH. So what does that mean? If we look at this, all of this indicator here, from this range, for methyl orange, the range for here is colorless. So what does that mean? If you have a solution that in the range of 0 to 3, there's no color if you have this indicator in it. Or you have phenolphthalein where from here to here, that would be colorless as well. So different indicators have different range of colorless and a range of color. But what happened when you bypass this, right? This is also colorless as well. So this range of color is happen in a specific range of pH for a different indicator. So this is colorless as well. Now, what's so special about this is basically when the color changes, assume that I use a specific amount of base with known molarity, okay? In this case, I use from 100 to 50. You see that change of volume right there? Okay? Basically, you take your initial minus your final, or final minus initial. It doesn't really matter. But this change is an absolute value change. That means it is a positive. How much volume is being used? So it has to be a positive number. And of course, the volume used is going to be 50 milliliter. Just happened because I decided to use 50 milliliter as. So this is your final reading before this color changed. So I'm going to change that to a different color. How about that? So it's going to change color. And the color changes based on the different type of indicator that you use, okay? And what's so special about this? Now let's continue to look at this example, looking at what type of data that we get from this process of titration. Now, I'll let you know that this solution that we are titrating with unknown molarity is an acidic solution. And of course, if we look at this graph, we can actually tell that it is titrating an acidic solution. How do I know? You can look at the pH right here. This range right here, it is acidic. And up here, it is basics. So it was starting from a very low pH. This tells you that it is acidic. Okay? Now, as I'm adding the base to this acidic solution, guess what happened to the pH? Of course, it's going to increase. As we mentioned before, as it go up higher and higher on the pH scale, it's become more basic, okay? So, as you adding more pH, we're reaching one important point right here. This is known as the half equivalent point. Think of the term half. What are we titrating? When we talk about half, we talk about half of the acidic solution in terms of concentration. And what's so special about the half equivalent point is that the concentration of the acid is equal to, notice how we have half, that means half of this concentration of acidic solution is titrated to its conjugate base. So the concentration of the acid is equal to the concentration of its conjugate base form. Now, why is that important? And if we look at the logarithm rule, basically if you have the log of 1, this is basically pretty much just log of 1. And basically log of 1 is equal to 0. Now, why is so special about the number 1? Well, number 1, or the number 1, indicate that the top part is equal to the bottom part. Well, in this case, at the half equivalent point, we have the concentration of the acid is equal to the concentration of its conjugate base. So what does that tell you? So in this case, you have pH is equal to pKa at the half equivalent point. So from here, you have pH equal to pKa. If at the half equivalent point, the pH is equal to the pKa, what about from here to there? Well, of course, right here you have your concentration of acid is greater than your conjugate form, which is the conjugate base. Okay? Now, numerically or mathematically, we can actually prove this using the Henderson-Hasselbalch equation. Well, if we look right here, if it's less than, let's plug in a value that's less than the acid. In this case, we have 5 relative to 10. And if you plug this into a calculator, it's equal to a negative number. So if you have a negative number, guess what happened when you have Kb plus a negative number? Well, of course, if this is a negative number, we have a values plus a negative number. In order for both sides to be equal to each other, your pH must be less than your pKa. Okay? So, on the multiple choice, if I give you information about pH greater than pKa, you have to be able to relate to the concentration in terms of this part right here. Either acidic solution or basic solution. Now let's look at the other case where what happened if we have this range right here. Well, of course, in this range, after we pass the half equivalent point, the concentration of the acid will be less than the concentration of its conjugate base form. And we can prove that mathematically using the Henderson-Hasselbalch equation. Just plug it in. Assuming that the concentration of this is greater than that, I give myself 20 over 10. And if you plug this into the calculator, it gave us a positive number. Now, if this is a positive number, we have a number plus a positive number. order for both sides to be equal to each other, the pH must be greater than your pKa. And as we continue to titrate, that means we add more volume of the solution, in this case the base. What's happening is, of course, the pH is going to get higher. And notice how right here you have that slope right there, very steep slope. What's happening here is right before this, right before the last acid is being titrated with that base or reacted with that base, you have a sharp increase in pH. Okay? And how it works is that the last pH is being neutralized. Of course, the pH is now going to go up by a lot faster. Because now what happened then, if you have no more acid in there, you're going to have the base, right? And when we have the base, we have this range of from 7 all the way to 14. And that's the reason why we have that sharp increase in terms of pH. Because the last acid is being neutralized. And if there are no more acid left in the solution, the pH is going to go a lot higher. But before we go all the way to the pH of 14, we pass a point called the endpoint. And it's also known as the equivalent point. So this is the endpoint, okay? And what's so special about this endpoint is this right here. It's basically, at this endpoint, we have added enough base to neutralize all the acid. And what does that really mean? Well, that means there's no more acid left. That means all the acid has been used. Because all of it is being used up, the number of moles of H plus is also equal to the number of moles of OH minus. But most importantly, is that the number of moles of acid is also equal to the number of moles of base. And what does that tell you about this? Well, now we can use that as a ratios in a chemical reaction. And I'm going to show you a calculation behind this later on, okay? But for now, we just have the number of moles of acid equal to the number of moles of base. And of course, what happened after we pass this endpoint? Of course, in this case, because we're titrating the acidic solution, now there is no more acid left. In this case, HA. And because all the acid are being neutralized, from after the endpoint, in this case, you just have the base that's being added to it. So, and that's the reason why we have the pH of all the way to 14. And if we look at the buffer solution, at this range right here, you have the buffer region. This is where a huge resistance of pH changes. Okay, so a buffer region allows us to resist changes in pH. So resist. Now, if we look at a titration of a base with unknown molarity, we're going to see something very opposite of the titration of an acid with unknown molarity. And if you notice how the pH is starting from the top right here at a very high number because it is a basic solution. And then we have the same thing, the half equivalent point. And let's apply this in terms of the Henderson-Hasselbalch equation again. So here we have the Henderson-Hasselbalch equation in the base form. And we're starting, of course, because it is a base solution, we're starting from a very high pH. And as we're adding more acid, right, we're going to add acid. Of course, the pH is going to go lower. Before we go far down here, we reach the half equivalent point. But notice how it is relative to the concentration of the base and its conjugate form, the conjugate acid right there. So we have those concentrations equal to each other. Well, in this case, the pKb equal to the pOH, just like we have pKa equal to the pH. And in relative thermal concentration, what we're going to have here, before we pass that half equivalent point, right, we're going to have the concentration of the base is a lot greater than the concentration of its conjugate form from this point backward, okay? But if we pass that half equivalent point, now we have the concentration of the base is less than its conjugate form, which is HB plus. Okay, and you see that sharp term, or that sharp decrease, because the last base is being neutralized. So whatever you're adding now is going to be very acidic. And that's why you see that sharp and steep slope right there, because the last base is neutralized. Just like how over here we have that sharp increase because the last acid is neutralized, okay? And at this endpoint again, we have the moles of H plus is equal to the moles of OH minus. Also, number of moles of base is equal to the number of moles of acid right there. Isn't that nice? And this is happening in a chemical reaction. And then if we pass this equivalent point, what we're going to have here is basically no more base. So all the base has been neutralized, okay? And what you have left is only the added acid. And that's why you see the pH scale drop dramatically. And there you go. Now you have a titration curve of an acidic solution with unknown molarity, or the titration curve of a base with unknown molarity. And how is that related to the Henderson-Hasselbalch equation? And within the Henderson-Hasselbalch equation, how is that related to the concentration of acid and its conjugate form, or base and its conjugate form? Now let's go back to the very beginning. Notice how we have multiple indicators, right? So the question is, which indicator do we put in this solution? Because it has a different range of pH for its range of color. And the answer is this. Looking back at the Henderson-Hasselbalch equation, or the titration curve, at the equivalent point, or the endpoint, the number of moles of acid equal to the number of moles of base. And if we think this in terms of the Henderson-Hasselbalch equation, if the moles of acid is equal to the moles of base, guess what happened? This will completely eliminate it. So we are going to look at the indicator with the pKa that is about the same as the pH at the equivalent point. So we are going to use an indicator with the pKa that is about the same pH at the equivalent point. And that's the last piece of the puzzle.